All right, so once again, our goal is to learn about improper integrals, how to compute improper integrals in section 5.10. Improper integrals have to be written as a limit of a definite integral with finite limits. But the point is, because improper integrals in section 5.10, the way we compute them is to find limits of a function of functions essentially. We need to be good with finding limits, and one area that's very important for finding limits, and it's useful for some section 5.10 problems, is what's called L'Hopital's rule. So you have here a function. This function f of x equals the natural log of x over x minus 1. And let's say for this function, we are interested in finding the limit as x approaches 1 of the natural log of x over x minus 1. Take a look at that for a minute. Okay, so what does the numerator, the natural log of x, approach as x approaches 1? What does the numerator approach for this limit as x approaches 1 of the natural log of x over x minus 1? What's the numerator, the log of, well, let me add, what's the denominator go to? X minus 1 as x approaches 1. What's the denominator? What number does it approach? Good, Mohammed. The denominator has to approach 0, right? Because 1 minus 1 is 0. What about the numerator, the natural log of x? What's the natural log of 1 equal to? What's the natural log of 1 equal to? 0. That's right, Jasmine. Good. So you have when you compute this limit, you have the top function approaching 0 and the bottom function approaching 0. The log of x approaches 0 as x approaches 1, and the denominator x minus 1 approaches 0 as x approaches 1. And so this is what's called an indeterminate form. Okay. In other words, let me just take off a little bit here. Hold on. Give me a moment here. I want to remove a few things here. So, yeah, the value of this limit of the natural log of x over x minus 1 as x approaches 1 is not obvious, because both the numerator and denominator approach 0, and 0 divided by 0 is simply not defined. So, and yet these kind of limits we need to try to find. Okay, so they mention in general, if you have the form where you have the limit of a ratio of function f over function g as x approaches a, and both those functions approach 0 as x approaches a, then, well, the limit may exist, it may not exist. You have what's called an indeterminate form. Okay, now you've seen indeterminate forms a little bit. Okay, so like for instance, this is a very famous example. If you have the limit of x squared minus x divided by x squared minus 1, and you let x approach 1, okay, the numerator and denominator both approach 0 as x approaches 1. But you can factor the denominator, you can factor the numerator, and then through simplification, you get the limit being equal to a half. How many recall problems like that from Calculus 1 in the highlighted gray box there? It's maybe been a while, but how many recall computing limits like what you're seeing there? Okay, Dawood remembers, and Avery remembers, and so that's good. That's good. Well, and so that's very nice. How many remember? Well, that's very nice. But the thing is, that's not going to help us. That's not going to help us compute this limit here. Because you can't, the log of x, you can't factor that, x minus 1, there's nothing to factor. So the question is, how are you going to deal with a limit like you see there in the highlighted limit there? Well, we're going to use a rule called L'Hopital's rule. Okay, and let me just show you well, let me bring up the rule here. Incidentally, another thing too, you can have another type of indeterminate form where you have the function in the numerator going to infinity or negative infinity, and the function g in the denominator going to infinity or negative infinity. That's also an indeterminate form, okay, because infinity over infinity is undefined. And what really determines whether a limit exists or not, when you have a ratio of two functions with an indeterminate form, is the rate at which these functions approach their limits. And this is really central to L'Hopital's rule. So L'Hopital's rule is, in section 4.5, and what it says is, let's say that you have two functions whose in their limit they approach 0, or two functions in their limit they approach plus or minus infinity. If you want to find, okay, the limit of the function f over the function g as x approaches a, it turns out that's equivalent to the limit of the ratio of their derivatives as x approaches a. An absolutely amazing result, but it's true. But it's absolutely true. So, initially this might, not, why is it true? Why would that be true? Okay. Now remember this L'Hopital's rule in the highlighted gray box, it's only for when you have indeterminate forms. That means you have 0 over 0 or infinity over infinity. Okay. So, or, plus or minus, you know what I mean. It could be plus or minus infinity over plus or minus infinity. That's an indeterminate form as well. So how are they getting this L'Hopital's rule? Well, let me show you. So you see here in figure 1, you have two functions. You have a function f and a function g, and you have an x value of a. Now f and g, what do f and g in figure 1 equal when x equals a? What's the value of functions f and g at x equals a? Based on the picture, the top picture in figure 1. Well, let me ask you this. Hold that thought, Mohammed. At x equals a, what's the y value? So all right, so you see that point there. You see that I want to say this the right way. On the x-axis, at x equals a, what's the y value for function f equal to? So x equals a, what's the coordinate? What's the coordinate for the pink f function at x equals a? That's right. So Mohammed, I would say a comma 0. But yes, the y, so function f and function g at x equals a, they both equal 0. So the f is approaching 0 as x approaches a. Okay, function f in figure 1 at the top, you can see function f approaches 0 as x approaches a, and function g approaches 0 as x approaches a. So these two functions, they're both approaching 0 as x approaches a. Now, what we can do with the functions is we can say, well, let's focus very close to the neighborhood where x equals a. Any curve function, if you focus on a very small part of the curve, the curve's going to look straight, like a tangent line, right? And so what they've drawn in Figure 1 on the second picture is they've drawn equations for the tangent lines for functions f and functions g at x equals a. That's what they've done. So I think you agree that the second picture in Figure 1, those are tangent lines, right, for f and g at the point at when x equals a. But the equations of those tangent lines are as you see. Y equals m1 times x minus a, and y equals m2 times x minus a. Now, I just want to show you how they're getting that. Let me bring up the whiteboard here. Whoops, hold on. Yep, let me bring up the whiteboard. So we're trying to motivate what we're seeing there in Figure 1. Okay, so let me bring this up. Okay, we have an x-axis and a y-axis. Okay, and I'm going to draw a, well, shoot. Come on, give me straight here. I'm going to draw a line. And the line's passing through A. And this line here, this y line, let's say the slope is m. So this line here, sorry, I'm trying to make it a little longer. This line here has some slope m, and I'll be consistent with the book. I'll say it has slope m2. Now the line itself passes through the coordinate a, comma 0. So if we wanted the equation of the line, we would say, okay, we would use the point slope formula. Y minus y1 equals slope m2. We're calling it m2 here. Hold on. Hold on. Okay, so it's slope m2 times x minus x1, point slope formula. So the coordinate here that's on that line is a0. So y minus 0 equals m2 times x minus a. Therefore, y equals slope m2, whatever it is, times x minus a. See that? So if we go back to the picture now, in the ebook, in Figure 1 there, from section 4.5, the blue tangent line has equation y equals m2 times x minus a, and the red tangent line has equation y equals m1 times x minus a, where m1 is the slope for that red tangent line. So the functions f and g look, if you're very close to that, if you zoom into that coordinate a comma 0, the functions f and g look linear, and so we could study the ratio of the functions f over g by looking at the ratio of those tangent lines, and that's where L'Hopital's rule comes in, because take a look. If you look at the slopes of those, I want to say this the right way. Yeah, if Okay, so right, this is fine. So if you put the equation, the tangent line equation for f, and divide it by the tangent line equation for g from figure 1 there, what happens is the x minus a's cancel out those factors, and you get m1 over m2. And this suggests, and m1 and m2 is just the derivative of the tangent lines at the point a0 for f and g respectively. So therefore, this justifies intuitively why this L'Hopital's rule is correct. Okay, was that helpful to see that? Maybe give me a thumbs up if you're comfortable with that. At least the idea intuitively. Okay, who's okay? We're going to look at some examples, but at least intuitively, how many are reasonably comfortable? Okay, it's good. Okay. Maybe somebody else. If don't be shy. John, how are you feeling with it? Okay. Franklin, how about you? Are you reasonable? Are you sort of seeing the idea here behind it?
Professor, I'm just thinking about that.
You're thinking about it. Okay, that's fine. Okay. Well, it'll take a little time to think through, but if you rewatch the recording, all the you know, when you know, right now I know you're focused on maybe some other things, like the exam, but when you watch the recording, I think it'll be you'll a second look at it, you'll see what I mean. So now we have L'Hopital's rule. So let's go ahead and look at some problems here. Okay, how many remember doing this problem in their Calculus 1 class? It's sort of a classic problem where you can use a geometric argument to find the limit. How many of you kind of recall this problem? Maybe in Calculus 1. The limit of sine of x over x as x goes to 0. Okay, Avery remembers that. And Franklin remembers that. Okay, and if you probably remember the geometric argument, it took a while to get the result. Well, we're going to get the result pretty quick here. Let me give you a moment to copy this example down, and then we'll go to the solution. When we look at this problem, okay, what does the sine of x approach? As x goes to 0, what does the sine of x go to? Well, it would go to the sine of 0. And what's the sine of 0 equal to? Good, Mark. Good, Franklin. 0. Okay, now on the other hand, let's look at this function x. So you see what you have here is you have a function f over a function g. What is g? What is your g function? What does x go to as x goes to 0? What does x approach? It approaches 0 as well. That's right, Gabriel. So you have a numerator that approaches 0 as x goes to 0, and you have a denominator function that approaches 0 as x goes to 0. And that's exactly right, Franklin. You have an indeterminate form. You have an indeterminate form of 0 over 0. And this indeterminate form is one where we could apply the L'Hopital's rule. Okay, so let me go to the next page and show you the solution. So by L'Hopital's rule, okay, and again, what I'll do is I will, here's function f. Here's function g, that's x. And the indeterminate form is 0 over 0, so I'm going to apply the L'Hopital's rule. And when I apply L'Hopital's rule, I put an equals above, I put an H with a circle on it above the equal sign. That's standard. So applying L'Hopital's rule, now the limit of this function f over g is the same as the limit of function f prime. Should put it in blue, right, to be consistent. It's the ratio of this function f prime over function g prime. So f prime, the derivative of sine is cosine, and the derivative of x is 1. And so now you have the limit of cosine of x as x goes to 0. If we now take the limit, that's just that. What is that? That's just the cosine of 0, right? And that equals 1. See how fast that was? Are there any questions? All right. Well, let us go ahead to the next question then, if we're good with this. Let's look at another example. Okay, so let me give you a moment to copy this example down. Okay, so this is an interesting problem. We have two functions here. We have this function x, and that function x is being multiplied by the sine of pi over x. So, and now we're looking at x as x going to infinity. So as x goes to infinity, well, this x would go to infinity, right? But what about the second function? What about the second function, the sine of pi over x? What's the sine of pi over x going to go to? Well, if you think about the sine of pi over infinity, okay, that's equal to the sine of what value? That's right, Gabriel. That's very good. That's the sign of 0, which is just 0. So here you have a function that's going to infinity. That's right, John. You have a function going to infinity, and you're multiplying it by a function going to 0. So you have a function that's getting big, and you're multiplying by a function that's getting small. And the question is, what's that limit? You have two functions that are sort of fighting each other. And if there is to be a limit here, then it's going to depend on the rate at which the function x goes to infinity and the rate at which the sine of pi over x goes to 0. But in this problem, we can't use L'Hopital's rule directly, because L'Hopital's rule is good if you have a 0 over 0 indeterminate form, or if you had an indeterminate form of plus or minus infinity over plus or minus infinity. So I have to manipulate this limit. I have to algebraically rewrite it so I could get it as a ratio of two functions, and hopefully the behavior will be one of those two indeterminate forms. So let's go ahead to the solution and see what we do. So okay, here we are. We have the limit as x goes to infinity of x times the sine of pi over x. And what I'm going to do is I'm going to multiply by 1 over x on the top and 1 over x on the bottom. I'm not changing the limit because 1 over x divided by 1 over x is equal to 1. So I'm not changing the limit. I'm just rewriting the expression there. Now you might wonder why do I choose to do that? Well, I'm hoping to get an indeterminate form like perhaps 0 over 0. So let's see if this worked. So the x's here simplify, and now our limit is as you see here. As x goes to infinity, what does 1 over x go to? What number does 1 over x approach as x gets large, as x goes to infinity? Take 1 and divide it by a very, 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 very big number. What's that going to equal, basically? So I need an answer. Okay, that's right, Susanna. That's going to go to 0. Very good. Now, what about the sine of pi over x? What's that going to approach? That's going to approach the sine of 0. But what's the sine of 0? 0, right? So now you have a function f over a function g, and you have an indeterminate form of 0 over 0. And so now you are able to use L'Hopital's rule on this to try to find the limit. So it worked. Strategy worked. But of course, before I take derivatives of the numerator and denominator functions, I'm going to write pi over x as pi times x to the negative first, because then I don't have to use the quotient rule, right? And the denominator I'll also write as x to the negative. I'll write that as x to the negative first. Now I apply L'Hopital's rule, So a big H over the equal sign. And the derivative of the numerator, well, I'm going to have to use the chain rule, aren't I? That's going to be the cosine of the angle pi times x to the negative first times the derivative of the, so you have the outer function, which is the sine. Inner function is pi times x to the negative first. Derivative of sine is cosine, so you get, for the numerator here, cosine of pi times x to the negative first power. And then the derivative of pi times x to the negative first power is just negative pi times x to the negative second power. Okay, so hopefully nothing fancy here going on. Now, nice things happen. You can simplify these x to the negative seconds out. And of course, a negative over negative is a positive. And you're left with the limit as x approaches infinity of pi times the cosine of pi over x. Okay, well, that would just equal, if we took the limit, that would just equal pi times the cosine of 0, because pi over x approaches 0 as x goes to infinity. So pi times the cosine of 0 is pi times 1, and you get pi. Okay, are there any questions on this one, on this problem? So you're a little more quiet today than normal. I hope everybody's, comfortable. Xavier, how are you doing? Are you comfortable with what you're learning here so far? Or Javier, I should say. Excellent, excellent. Okay. Clea, how about you? All right, well, Neon, how about you? Are you okay? Reasonably comfortable? Man, I'm getting worried. I'm getting worried. Susanna, how about you? Are you okay?
Hi. Little trouble cramming more information in my mind with worrying about the tests. I will go back and watch this recording.
Okay, very good, very good. All right, well, let me keep going then. Let me keep going. So, all right, let's do another problem. Let's do another problem. Let me give you a moment to copy this. Okay, so let's see here. So the secant of x, What's the definition for the secant of x? That's right, that's right, Gabriel. That's 1 over, that's right, Javier, 1 over the cosine of x. So here, well, and the tangent of x, the definition of the tangent of x, of course, we know that as sine of x over cosine of x. So what's happening here? Well, 1 over cosine of x, as x approaches pi over 2, the cosine of pi over 2 is 0. So this function here, secant of x, it has an asymptote at pi over 2. That's why you're going from it's not a two-sided limit. The little minus sign there means you're approaching pi over 2 from the left. So 1 over the cosine of x approaches infinity. And the tangent of x also has an asymptote at pi over 2. So the tangent of x also approaches infinity. So in this situation, okay, you have an indeterminate form where you're taking a function that goes to infinity and subtracting another function that goes to infinity. But again, that doesn't mean that the limit equals 0. You could have, depending on the rates at which these functions approach infinity, you could have you could have like a non-zero limit. So what do you think might be a good strategy to do? Again, if I'm going to use L'Hopital's rule, I need to have a function f over a function g. So what might be a good strategy to do with these two fractions that have the same denominator? What could we do with them? Can we subtract them? Well, the denominator is the same, right? So we ought to be able to subtract those two functions, and that's gonna help us. So let me go to the solution on the next page here. Let's take a look at it. Please let me know if you have any questions. Okay, so now we have here, we have 1 minus cosine of x and sine of x over cosine of x. They have the same denominator, so we could write that expression as 1 minus the sine of x over cosine of x. And now this is very good because we have our function f in the numerator, function g in the denominator, and f approaches, well, g approaches cosine of x, approaches 0 as x goes to pi over 2. And the function f will approach 1 minus, well, let me be a little more clear. So function g will approach the cosine of 0, which is 0, which is, sorry, I'm not doing this right. Let me do it again. So this is my function g, and this is going to approach the cosine of pi over 2. which is 0. Now my function f is 1 minus the sine of x on top. And as x approaches pi over 2, that's going to approach 1 minus the sine of pi over 2, which is 1 minus 1, which is 0. And so you have another indeterminate form, 0 over 0. You can apply L'Hopital's rule. And that's what I do right here. L'Hopital's rule says the limit of the ratio of f divided by g is just the limit of the ratio of f prime divided by g prime. Well, the derivative of 1 minus sine of x is minus cosine of x. So that's your f prime. And the derivative of cosine of x in the bottom there is negative sine of x. So that's your that's your g prime. Now here, this is just going to equal, if I take the limit, I can do it because I'll have the cosine of, just separate this a little bit now. I'll have the cosine of pi over 2 in the numerator, negative cosine of pi over 2, and then I'll have negative sine of pi over 2 in the denominator. And so the sine of pi over 2 is 1, cosine of pi over 2 is 0, our limit's going to equal 0. So what's happening is the rate at which these two functions approach infinity is, they're going to infinity at the same rate, essentially. And so the infinities cancel. But, you have to use L'Hopital's rule. Are there any questions at all? Gabriel, how do you feel about this? Are you feeling all right with the material? With L'Hopital's rule? Okay, good, good. Avery, how about you? Are you, I mean, I know it's new, but are you okay? Good. Dawit, how about you? All right. Well, I know Dawit is here or was here, but we'll ask later. Okay, let's continue. Let's do one more. So I want to give you a little break here, but I want to do one more example. So I'm going to do one more example, give you a break, and then we're going to do another example from section 4.5. But let me go to this next example. Let me give you a moment to copy this one down. Daniel, how are you feeling about the material? Mark, how are you feeling? Are you reasonably okay? Okay, very good. All right. And Masume? Okay. All right. That's all I ask. All right. All right. So these L'Hopital rule problems are really, they're in a sense almost like little puzzles that you have to solve. And this one here, it may not be obvious what to do, but again, we need to have a ratio of two functions f over g. Okay, I have the difference of two functions here, but what we can do is we can factor an x here. We can factor an x. And so we have the limit of x times the quantity e to the 4 over x power minus 1. Okay. So let's see how that helps us. I'll go to the solution on the next page. Let's take a look. So I do the factoring here. And okay, so again, what we want, we need to get a function f over a function g. So I can use the same trick I used before. I can multiply the numerator and denominator by 1 over x, which is just 1. And then in the numerator, the x's simplify out. And so you're left with this limit here. Okay, the limit as x approaches infinity of e to the 4x minus 1 divided by 1 over x. Let's take a look here. Now, 1 over x, what does it approach as x goes to infinity? What does the denominator 1 over x approach? What value? So take 1 and divide it by a very, 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 very big number. What's that going to be about equal to? 0. That's right, Mohammed. That's right, Mark. 0. So this 1 over x approaches 0. E to the 4 over x would approach e to the 0, which is 1. So in the numerator, you have 1 minus 1, which is 0. And in the denominator, well, no, I want to say this the right way. In the numerator, I mean, we know the denominator is approaching 0. And the numerator is also approaching 0 as x goes to infinity. So here it is, the indeterminate form 0 over 0. And I'm going to use L'Hopital's rule. But of course, I'll write the numerator. I'll write that 4 over x as 4 times x to the negative first power. That's my function f. And then my function g down here, x to the negative first, that would be my g. I apply L'Hopital's rule, take the derivative of the numerator and denominator. Let me know if you have any questions. Okay. So we'll get then simplification here, and the limit as x approaches infinity of 4 times e to the 4 over x. It's just 4 times e to the 0. And so you will get 4. You'll get 4. Really an amazing, how many find this sort of amazing what we're doing here? Yeah, the L'Hopital's rule, or at least interesting. Okay, Susanna likes it. Was hoping maybe I'd get a few people. Who's sort of a little bit nervous about L'Hopital's rule? Don't be nervous. It's a good thing. It's a good thing. Okay. All right. So, Javier, how do you feel about L'Hopital's rule? Is it kind of interesting to you? Okay. All right. Okay. All right. Jasmine, how about you? It's all right. Okay. All right. I'll take that. I'll take that. All right. So I want to do another example, but let's go ahead. Let me stop the recording here, and we'll take a break, and I'll do the next example after the break here. So let me stop the recording.